So welcome to this episode 12 of our story, and most likely this will be our final episode for this series also. And today's hero is Robert Millikan, and you must have known his name because of his famous oil drop experiment. I might have mentioned earlier that he designed this experiment to measure the charge on a single electron. So in many of the universities, Indian universities too, we have this experiment in our MSc syllabus, and we enjoy doing it. Now, Robert Millikan has done a series of experiments on photoelectric effect, and especially after Einstein's work, because somehow the physicists that time were very skeptical about this Einstein idea of localized energy packets in radiation. This is because this interference, diffraction, all those things have established so well that the entire energy of this electromagnetic wave is distributed continuously in the wavefronts, and so any kind of localization, discretization, going again for that particle model, corpuscle model, was very difficult for people to accept. And Millikan was a great experimentalist. So just after this 1905, he started designing experiments with all kinds of accuracy demands, and any kind of source of error to be eliminated. Meticulous experiment he was trying to perform so that unambiguously he could refute the prediction of Einstein that the energy is linearly related to the frequency and all those things from that corpuscle type of model, photon type of model. Radiation is composed of discrete energy, quanta, those kind of philosophy, those kind of assumptions. And in this effort, he designed several kinds of operators, and then improved upon that, and eliminated sources of error. And for that he was a hardcore experimentalist, and I will say that an excellent experimentalist, taking care of every minute thing. Finally, he has published this paper in Physical Review, and that was in 1916. I'll give the reference, and I will be describing little bit on that paper, especially the vacuum tube that he has designed, or the apparatus that he has designed, has many very special characteristics. So I will show you that diagram that he has put in his 1916 paper in Physical Review, and then based on that diagram I will describe what it is. So let's go to our screen. So this is that diagram, and it says that it is the ninth vacuum tube that he has fabricated. So he was working on it from 1905, 1916 he is writing this paper, and 9 times he has changed the apparatus. So you can just see how much he has concern for removing all sources of uncertainty to the maximum possible. So finally this design comes up, and let me explain what it is in the next slide. So here you see on the right side emitter, sodium, lithium and potassium. There are 3 cylinders mounted on a wheel. One is of sodium, one is of lithium, and another is potassium. He has worked with sodium and lithium and not with potassium, though he had planned to do that. Now this wheel can be rotated to bring the desired cylinder in front of the light source. This cylinder on the right, on which I have put that line saying that this is emitter, that is in the right position. The light will come from the right and fall on its surface. Now this wheel, how to rotate this wheel to bring the other cylinder in this position? For that he has magnetic coupling. He has magnetic coils, current carrying coils on the outside of this vacuum tube. Remember, this everything that I am showing is inside a very good vacuum, and all this rotation and everything has to be done inside that tube, but then it has to be controlled from outside. So from outside he is producing those magnetic fields which he is controlling, and then inside also he has the corresponding electromagnets or circuits, and using that interaction he is able to rotate this wheel and bring the appropriate emitter in front. Now on the left also you see electromagnet. In fact, a diagram shows that yes, there is some magnetic thing, some coils and some circuits. Now that knife, focus on that knife that I have written. A small knife is there, and that knife is mounted on some structure, and this electromagnet or the magnetic coils which are there will be used to push this whole structure towards right. So what is this all about? Why this knife is inside the vacuum tube? Because the photoelectric effect pertains to the surface of the metal, and if it is sodium, it should be sodium. But whatever is that residual air in this tube, this metal surface will get oxidized at the surface. Now if the surface gets oxidized, the entire character is changed, and you don't have much control. Gradually it oxidizes, and it's a time dependent function. So every time the experiment is done and the data taken, that surface has to be cleaned, and this knife is for that cleaning. So the wheel will be rotated and the appropriate emitter will be brought in front of this knife, and then from the left magnetic coils, this whole structure will be taken towards right, and then it will scrap that surface layer from that emitter. So those are the kinds of care he is taking. So in this slide you can see the path of light that is shown. It enters from a particular window from right, and this dashed thing where Faraday cup is written, this is an oxidized copper cylinder in the form of a wire gauze or a mesh, and this is actually the collector. So this sodium or lithium, whichever emitter is used, first that is cleaned by that knife. The knife is taken back, the wheel is rotated so that it comes in front of the light, and then the light falls on the emitter. And then the electrons which are ejected are collected by this Faraday cup, which is this oxidized copper cylinder, and which is connected to that circuit. The electrodes are there at the bottom, and that is how the whole thing is completed. Now, how many electrons are being collected by this Faraday cup, that is measured, and through the current which goes through that emitter circuit, and that is how the photocurrent is measured. Now in this next slide you see I have written to measure contact potential on one side, other side it is oxidized copper, and that indicator is on a line where in small letters S is written. So this is a plate, oxidized copper plate, and I'll tell on the board what it is all about. So let us talk of contact potential. and this term comes into picture when you have two different metals electrically in contact with each other. So I give you an example. Suppose you have some plate A, metal A, some plate which is made of a metal A, another plate made of some other metal, say B. So you have two different kinds of metals here, maybe one copper, one zinc, or any two. Now, as long as they are not in contact, fine. But suppose they are put in contact. Suppose this a wire of material B is properly connected between these two. Suppose this is wire of that same metal B. So, at the junction, since the two metals are different and they are all electron density and all those things are different, so there is a flow of charge from one to the other, and some charge appears here, some charge appears here. Positive and negative equal and opposite, because total is of course neutral. Alright, so suppose some positive charge is developed here, some negative charge is developed here, and if you talk in terms of potential, if this potential is 0, we have not put any battery or any source. This is 0, this is 0, this is 0, this is 0, but right on the other side we will be K, and that we will be K everywhere. That we will be equal to K everywhere, and so on. So this whole thing is at one potential, then there is a jump in potential, and then this whole thing is at one potential, and this potential difference across the junction depends only on the nature of the material. Only on the nature of the material. What metals are here and here. Alright, so now is known as contact potential. This K is known as contact potential. And how do you measure? How can you measure? Various ways. One way is that the charge that appears here and the volt that appears, the potential difference that appears here and therefore here. And then you have some capacitance. Right? You have some capacitance. So you will have this Q equal to CV relation. Now this V is fixed. This V is fixed. This junction will decide how much is this V. Now if you change the separation little bit, what are you changing? You are changing the capacitance. Parallel plate capacitor, some epsilon naught A by D. So if you change the separation, the capacitance changes, the contact potential still remains the same, so this will remain the same, and therefore this charge will change. You will have more positive charge or less positive charge here, and so on. If the charge changes, this charge, the magnitude of this charge, value of this charge changes when you are doing the separation, you are changing the separation. That means charge is flowing. Okay? If more charge is coming here, it means some charge is flowing from here. And if it is flowing from here, it is flowing from here. So in this circuit, there will be a current. Now if you can measure that current, and then you can relate how much I am changing the separation and how much current is being produced, and therefore how much charge is going in a certain time interval. From those things you can calculate this contact potential. Now that we know that this kind of thing is there, let's look at that photoelectric Einstein equation once again. So let us consider a typical photoelectric effect experimental setup. You have an emitter, then you have a collector and a light source, and then electrons are coming out. And here you have a potential difference applied between this collector and the emitter, and this voltage, the positive voltage on the emitter, so that the electric field is in this direction, which will oppose the motion of this electron. So it is kind of retarding potential. So if this battery or whatever you are using arrangement, if this voltage is V0, suppose this is your grounded, so this is V equal to 0, and then you have V equal to V0 here, and then you say that okay, the maximum kinetic energy, half mv square, which is equal to h times mu minus w, what function? Frequency of the light used, and then there is the maximum kinetic energy of the electrons. So the Einstein equation, according to the Einstein equation, and if you apply sufficiently large V0 so that these electrons do not reach the collector, then the current will be 0. To stop the current, what is the minimum potential you have to apply, stopping potential? If that is V0, if V0 denotes this, then this half mv square is equal to E times V0, and that is hv minus w. And therefore, if you plot this V0 on the vertical axis and this frequency nu on the horizontal axis, you will get a straight line, and the slope of that straight line will be h by e and all those things. Okay, so that is that comes out from the Einstein equation. But the two emitter and collector are of different metals, and should be different metals. Millikan has taken care of which material should be here and which material should be here, because if you take the two from the same material, then light which is reflected from the walls, if you are sending light, then not all the light is getting absorbed. Alright, so a lot of light is reflected from here, from here, from here, from here, and if that light falls on the collector, that reflected light falls on the collector, and electrons are ejected from this side also, then the equation will not work. And so they are dissimilar material. This frequency should be able to eject electrons from here, but the same frequency should not be able to eject electron from here. So you have to choose the material properly, and Millikan has taken care of all these things. Okay, now if it is dissimilar, suppose this collector and this connecting wires, they are of the same material, but then this is different. So what will happen? Potential here is V0, potential here is 0, potential here is V0, potential here is V0, but potential here will be V0 plus K, because here we have a junction of different kinds of material, so the contact potential difference will be there. This side it is V0, and therefore on this side it will be V0 plus K. So what the electron will see? Electron will see that there is a potential difference of V0 plus K, and hence this V0 should be replaced by V0 plus K, and therefore you should have E times V0 and plus K. This should be equal to h nu minus w. This modification is needed. Now Millikan uses this to give a further test to this equation, Einstein's equation. And how? Contact potential can be independently measured using the techniques that I had earlier discussed here, capacitance and then increasing the distance and so on. And he has arrangement for that in his vacuum tube. So contact potential can be independently measured, and from the Einstein equation one can get this contact potential. If they match, that will have another test for Einstein equation. Okay, so suppose you have a second material here. You keep this collector same, and then you take emitter number 2, which has a different work function, different contact potential from here, but you keep this light same and then find what is the stopping potential. So for that second material, it will be, say, stopping potential is V0 prime. When I change the emitter and use the same frequency nu here, then the stopping potential will be different. Let us say it is V0 prime. Remember, this V0 prime is the potential difference that I have applied. We have applied, alright, the cell here. So this is V0, and then when I change this emitter, then it becomes this. Contact potential is also different, and this is same, and work function is also different. Now you also know that there is a threshold frequency or threshold wavelength. If the frequency is less than threshold, then the photo emission does not take place. Whatever voltage you apply here, you won't have any emission if the frequency of this is less than a minimum. And that can also be independently obtained from this setup itself, from the experiment itself. You change the frequency, or you have those frequencies and then draw some graph of current versus something, and then you see where that graph tells that the current will be zero. So that minimum frequency is given by, say, W is equal to H times nu naught. This is the threshold frequency, H times nu naught, which can independently be determined. So if I put it here in place of this W, I write H nu naught. So let me write it H nu naught, and for W prime I write similarly H nu naught prime. So this is the threshold frequency for emitter 1, and this is threshold frequency for emitter 2. Now subtract these equations. What do you get? Subtract E times V naught minus E times V naught prime. So I am subtracting this from this, plus E times K and minus E times K prime. This is equal to H nu cancels out. Okay, so I can perhaps write here itself. And then this minus this, so H here, nu naught prime here, and minus nu naught here. This. And from here you can write what is this K minus K prime. Okay, so if I write E times K minus K prime is equal to H times nu naught prime minus nu naught, and then minus E times V naught minus V naught prime, like this, and divide by this E, so you get H by E here, and this E goes away. So now this K minus K prime is the contact potential between the material of emitter 1 and emitter 2, because K is the contact potential of emitter 1 with the collector, and K prime is the contact potential of emitter 2 with that collector. So if you subtract, you get the contact potential between emitter 1 and emitter 2 materials. Okay, so that contact potential can be obtained independently in Millikan setup, and from this equation, because you can measure nu naught, you can measure nu naught prime, you apply that V naught, and you know at what potential it stops the current. So these things are known. So we have two different ways. One is direct measurement of contact potential, and then second is from these parameters, and these two should be equal. If they are equal, that means this equation is valid. Alright, so Millikan does that also. So let me go to screen and discuss it further. So look at the right side, I have written oxidized copper, and then this indicator line is going to a plate where S is written, capital S is written. This is an oxidized copper plate. And in order to get that contact potential, this will be used as one of the plates. And then this particular emitter which is to be used, and after it is cleaned using that knife, this wheel is rotated and that emitter is taken in front of this plate S. So now, and then on the left side I have written to measure contact potential. So you have circuits there. So the capacitor is formed between the emitter and this plate S, and then by changing the distance between these two and measuring the current in this circuit which I am indicating on the left, one gets the contact potential. So in the same vacuum, in the same vacuum tube, in the same setup, the surface is cleaned, contact potential is obtained, and then this emitter is taken in front of the light source and photocurrents and other things are measured. So that is how he takes care of that contact potential. Or by knowing the contact potential independently, he tests that Einstein's equation. Now this is one of the graphs in that paper. It's full of tables and graphs. I'm just showing the one which shows you linear dependence of stopping potential with the frequency of light used, Einstein's equation, and see the experimental data are perfectly on straight line, linear. And from that line, slope of that line, he has calculated the values of Planck constant, and it turns out to be very, very close, which is written in this box in handwriting. So a lot of data are there, the variation with this voltage and everything is there, but I am just showing the one which is most relevant. Okay, so this is how he ends up in verifying Einstein's equation in a best possible manner, without any doubt, taking care of everything that was there in the world, and he finally verifies it. So you can appreciate how well designed was all this apparatus, and no wonder it took him 10 years to reach this perfection. And in this period, many more physicists performed experiments to verify this Einstein's predicted law of photoelectric effect, but the kind of accuracy, the kind of perfection with which Millikan did it was suddenly beyond doubt, and therefore the most reliable test. And when the actual experiment was performed, photocurrents were measured, stopping potentials were measured, frequency, he took that mercury lamp, and by using proper filters, he could he could stay away with the stray radiation. So almost monochromatic light he used, and so many lines and so many wavelengths, and he took extreme care of what is the stopping potential and the threshold frequency, and whether this collector is not emitting electrons because of reflected radiation that falls on that. Everything taken care of, and results were in beautiful match with Einstein's prediction. Beautiful match with Einstein's prediction. Millikan was very critical of the theory, the philosophy of Einstein, that radiation energy is localized in different packets of h nu. So he was absolutely not ready to accept that, and even after even after this most successful verification of Einstein's equation, Millikan had reservations in accepting that photon theory. I will read some lines from his paper showing his concern about the theory. But then when Millikan himself was awarded Nobel Prize in Physics 1923 for working on the electron, the measuring charge of the electron, and doing such a beautiful, wonderful experiment on photoelectric effect, by that time he had accepted, or he was convinced that okay, maybe nature is like that. So that is the story of photoelectric effect. And once this 1916 this Einstein's prediction was verified, then the scenario changed very rapidly. Although Millikan himself was not convinced, even in the writing of 2000, this 1916 paper, I will just read some lines before I leave. But the scenario changed so fast, and people started appreciating Einstein's insight and his ability to think and come out with very bold hypotheses, very different hypotheses, contrary to all beliefs, all traditions and all those things. And he was awarded Nobel Prize in Physics 1921, for which we are now celebrating his centenary year. So thank you very much. I hope this 12 lecture series was useful to you. Knowing the historical perspective, knowing the struggles, knowing the commitment, all those things is very inspiring. And as science students, as science persons, as science teachers, we should imbibe those qualities. Thank you very much. Okay, so before leaving, let me read 2 sentences from here. This is Millikan's paper, the same paper in which he has tested that Einstein's prediction in the strictest possible test, and found absolutely nice agreement and all that. But still, in the last section, this is the last section of that paper, he says, perhaps it is still too early to assert with absolute confidence the general and exact validity of the Einstein equation. And in this same paragraph here he writes, yet the semi-corpuscular theory by which Einstein arrived at his equation seems at present to be wholly untenable. Okay, so that was the scenario of 1916. So you can very well understand the acceptance and rejections and the struggle of Einstein's theory from 1905 to 1916 at least. And but then, as I said, the scenario changed so fast that by 1921 it was a very, very established. So thank you very much for attending this course.